I believe it's time to get started, especially since the lady announced that the recording is in progress. So, welcome everybody. My name is Roger. I'm sitting here in sunny South Florida where we don't seem to, well, we're not here to talk hurricanes as such, although the governor of North Carolina seems to be pretty well convinced that something's going on, because they've never seen any storm like that before. But in any case, we're going to talk about some of the facts that are well known and some of the things that engineers are doing and important things that are being done by engineers and architects to address this challenge. And of course, not everybody believes climate change is happening. And we'll save that one for another day. We're going to assume it is. And if it were, what would we do about it? And the fact of the matter is, what has been happening very aggressively, fortunately, and it's the thing that gives this old man some optimism that his great grandson in the year 2021 will, let's say the year 2100, how about that? We'll still have a planet to survive in. So let's take a look at what we've got here. We're going to talk about a couple things. We're going to talk about what's going on, how serious it might be. What happens when temperature rises? What can we do about it? What's going to cost? And some of the things that specifically can be done to fix it. This is not North Carolina. This is a previous situation. And there are some barriers that need to be overcome. We'll come to that at the very end. But first of all, let's get a little scientific basics for what's going on out there. And to start with, it helps to look at a definition between weather and climate. And if you go to the dictionary, it will tell you what weather is. If you look out your window, that's what the weather is. It's what's happening right now. And but if you look at what the weather does over a prolonged period of time, then that would be called climate. I've lived in South Florida for a long time, since 1969. In 1977, I witnessed a snowfall in my front yard. Never before, never since. Maybe before, but at least in 77, it was pretty unusual to see some snow actually accumulate in the front yard. And that was not a happy year for our mango tree or our orange tree. Recently, if you look at the ASHRAE charts for weather, now the lowest expected temperature in Miami is 5 degrees Celsius, which is over 40 degrees. And for that matter, as a year-round resident in South Florida, we have not seen a temperature below 40 degrees now in as many years back as I can remember, at least 10 or 15. High 40s is about where we go now. Summer, maybe up to 95. And I remember when I first came down, I tell my friends in Minnesota that summers were between 80 and 90 and winters were between 70 and 80. So there seems to be some changes going on here, at least short term, but then when you look at the causes, it leads to suspect that we may be into this situation for a little bit longer time. Let's take a look at greenhouse gases and what they do. And, you get a copy of this slideshow, and you're welcome to simply ask for it at the end of the presentation, and you can take this home and do whatever. But in any case, we're going to talk a little bit about light and the sun and sunlight and the atmosphere and a few things like that and what happens. We all know the Earth takes on radiation in the form of light and heat from sunlight. And at night, when it's dark outside, it can give off heat. And matter of fact, during the daytime, it even gives off some heat. It takes some on, it gives some off, because the black body radiation formula tells that radiated heat is proportional to the fourth temperature, the fourth power of the absolute temperature. So as long as we make sure that the amount we release is equal to the amount we absorb, then we're going to have relatively constant, predictable temperature range. And it's still going to be temperature range because of other weather and climate patterns, and the idea that the Earth is tilted on its axis and is in an elliptical orbit, a few other things. So in any case, most visible sunlight wavelengths are transparent in the atmosphere. Not all, but most. There are a few absorption lines from water vapor and a few from carbon dioxide. But when we look at greenhouse gases in the atmosphere, what they do is they reflect emitted radiation back to the surface. In other words, once the short wavelength radiation arrives at the surface of the Earth from the sun, and then warms the Earth of the surface of the Earth, then that reflected radiation, it's harder for it to get out. And so the only way to equilibrate that is for the temperature to rise a bit, such that the rate of radiation increases, such that that block that's trying to hold it back from the greenhouse gases has to be overcome. And the amount reflected back depends on the concentration of the greenhouse gas. And this is scientific fact. This is not something we can argue with. This is what's been observed, proven, and even put into formulation. So this is a fact here. And restore the equilibrium, as we mentioned, temperature has to increase. So if we look at the radiation spectra, and this is something that anybody who wants to have a little fun with their Excel, you can just plot the Planck's black body radiation formula. And if you plot radiation in terms of watts per square meter per meter of wavelength, and that's just a convenient scale for the vertical scale here versus the wavelength in meters. And notice we're pretty small meters here. We're really looking at micrometers and nanometers. Notice that the peak of this radiation here, and we're a log scale here, the peak is right around between 5 and 6,000 nanometer, or sorry, 500 and 600 nanometers, 5,000 to 6,000 angstroms if you look at units in angstroms instead of nanometers. In any case, here are two radiation spectra. This is the sun at 5,800 K, and here's the Earth at 300. So you notice that the peak intensity, for one thing, is 1, 2, 3, 4, 5, 6, almost 7 orders of magnitude less than the peak intensity of the sun. So thank goodness the sun is 93 million miles away, because if not, we'd be pretty warm. And so by the time the sun gets to the Earth, the intensity is a little lower, as we'll see soon. Here's our visible spectrum, okay? And here's the ultraviolet spectrum, and everybody knows about that. That's why we buy sunscreen. And here's the infrared spectrum. So got this radiation spectrum, and you can see the Earth is essentially completely in the infrared in terms of any re-radiated heat, whereas the sun, given when it warms up to 5,800 Kelvin at its surface, it's peaking out somewhere right around 2, 3, 4, 5, 5,000, or sorry, we already said that, 500 nanometers. Okay, so 93 million miles later, the intensity of sunlight at the top of the atmosphere is more or less 1,367 watts per square meter, give or a few thousandths, give or take a few thousandths of a watt. And by the time it gets to the surface of the Earth, about a third of it is absorbed, and the intensity is down to 1,000 watts per square meter at sea level. Of course, at 18,000 feet, where there's only half as much atmosphere, there's more intensity and more ultraviolet. And so when you're climbing those tall mountains, you got to be a little more careful with your sunscreen. Okay, so what about this atmospheric CO2 people are talking about? Well, there are some folks who've been measuring that at Mauna Loa for a long time. And here's their data since about 1959, and it's measured in concentration of carbon dioxide in parts per million. And note that we mark carbon dioxide here. This is essentially carbon dioxide or carbon dioxide equivalents. Some greenhouse gases are stronger than CO2, some are less strong. But we're talking not carbon, but carbon dioxide, but also CH4, another carbon compound, is a very strong greenhouse gas. And we tend to, and of course, CH4 is natural gas. And when that gets emitted in the atmosphere, until it converts down to carbon dioxide and water, it is a much stronger greenhouse gas. It takes around 10, 12, 15 years to break down. So right now, we are up in the neighborhood where the folks who study this say we are getting into a critical situation, because somewhere between 425 and 440, depending on exactly what criteria you use, there is great concern that we could reach a runaway situation, just like a nuclear reactor where you don't have it damped out properly. If you remove those control rods, once that reaction gets going, you can't stop it anymore. So we're looking at some interesting stuff here, and we'll look at some of the possible consequences. If you want more information on this, this is a very good reference here if you want to read an additional 88 pages. Okay, but we're going to leave it at this one page for today, just so you've got something to look at and see where we've been. I was born in 1943, so you can see where the carbon dioxide concentration was, and we had lots of nice snow when I was a kid back home in Minnesota. They had 3 inches last winter, according to my daughter, who moved back up there. So yeah, things are changing. So let's look at quickly 11 key tipping points that have been identified by the Job One for Humanity group. And these are some things. Everybody thinks of sea level rise, and some attention is now being paid to fires. And there's been a number of studies done that shows indeed the increase in forest fires is due to additional CO2 going into the air, and you can read studies about that as well. But let's look at these 11 points, because there's some here that a lot of folks haven't even thought about. I had not thought about it until they were brought to my attention in this particular article. Usually sea level rise, everybody thinks of that, everybody hears of that, but there are other things that can happen, and there's some kind of scary results that can happen. We haven't tried the experiment completely, and I'm not sure I want to be a part of that. In any case, there is a possibility of extinction level climate destabilization, and you'll be able to see where that might come from as we move through here. The first thing, and it's a surprise, total atmospheric water vapor, because obviously, it's pretty obvious, especially down in the Gulf of Mexico, as water gets warmer, it evaporates more. So there's more water vapor. And clouds, by the way, are actually very small condensed water vapor particles. Forget about the 539 calories per gram latent heat of vaporization. These clouds have already given that this is off, and as they condense a little more and more and more into droplets, then all of a sudden we get some rain. But the point is, atmospheric water vapor is in fact a greenhouse gas, and it can either stop infrared from coming in, or it can prevent it from leaving. So it's something that can change climate patterns. And who knows, you might even get a nasty flood in North Carolina as a result. And what happens? Well, more watery vapor. It's not, and I said 539 calories per gram. If we want to do BTUs per pound, we got 970. And if you condense it, it gives it off. And so when that water condenses, it gives off the latent heat of evaporation, and it warms its vicinity. So therefore, fortunately, clouds reflect back some sunlight during the day, but at night they act like a blanket. And so the more clouds, the more chance humidity reaches 100%. And we've had some interesting situations with that here in Florida the last few weeks. And And that's when our air conditioner in our building happened to decide it doesn't want to remove water vapor anymore. So some engineers are going to have fun trying to decide whether they want to replace our air conditioner for us. And that'll be a fun job, 45 tons of air conditioning. In any case, so water vapor is one issue. Melting ice is another one because ice itself loves to reflect sunlight back out, but as it melts, then the sunlight simply gets absorbed by the ocean. And then there's this third tipping point, the albedo effect. And that's simply when sea ice reflects sunlight back away from the Earth's surface. If there is none, then the sunlight is absorbed. I mixed those two up, didn't I? The melting ice, of course, as that melts, the sea level rises. So there's our ice shelves breaking and sea level rising. But then once this ice in the sea melts, rather than reflecting sunlight back away, more sunlight is absorbed. And this is, of course, happening up in the polar regions. And the more sunlight that's absorbed, the more water is heated and the more ice is melted and on and on. And tipping point number 4 is the melting permafrost, which is an interesting situation because there's a lot of methane trapped in the frozen permafrost, and along with maybe who knows what else. And since methane is 20 to 100 times more stronger than carbon dioxide as a greenhouse gas when it mainly when it first goes into the atmosphere, and that's where this 20 to 100 times, because the methane does break down into carbon dioxide and water within about a 10 to 15 year period. So in any case, methane is a dandy greenhouse gas, and greenhouse gases, more of them, more permafrost, more methane, and on and on. And so this is, some would say, serious. Number 5, plankton dying. All right, this is not coronavirus here. These are plankton, and plankton, there was once thought, we'll just dump a lot of this carbon dioxide in the sea because plants love carbon dioxide. Plankton love it, but when carbon dioxide goes into the ocean, it becomes slightly acidic. And plankton are not really happy with acid. So that's a bit of an issue. So what was once thought as a great idea of dumping carbon dioxide into the ocean is getting some second thought now. So because it's important because the plankton can be a major disruption in the oxygen cycle since they produce somewhere between 50 and 80% of the world's oxygen. I know it talks about the planet losing oxygen because of global climate change. But here you see how it can happen. If you kill off plankton, and they're a major oxygen producing factor, converting CO2 into oxygen, provided that the pH of the ocean is at an acceptable level, then we need to think about that. So I don't know, we dump a bunch of baking soda into the ocean to keep the pH up. Who knows? Somebody probably thought of that. Number 6, transfer of ocean surface trapped heat to lower levels. That can happen. And if the heat on the top goes to the bottom, then the cooler water on the bottom goes to the top and gets heated up. And so that becomes an interesting kind of a current circulation. And then there's the fires thing. And we know about that. We hear about every year, more and more. Western United States, Western Canada, other parts of the world. Then there's the deserts, and if you release carbon from soils, normally the soil stores it, but if it gets hot, then the carbon can be oxidized, and you get carbon dioxide release. So on. Number 8, and I'm not sure how many thought about number 8 as a thing. And then here's number 9, changes in major ocean currents like the Gulf Stream, which tends to be slowing down. which therefore is carrying less heat away from the tropics towards the north, which who knows whether that might be just diverting the path of some hurricanes into the Gulf rather than up the east coast of Florida. Good question. We may learn more about that over the next few years. But in any case, ocean currents are important. We've gotten kind of used to them, especially along the west coast of the United States. So, and then there's the global pandemic thing. I mean, when the permafrost melts, what else is in there other than the carbon dioxide? Well, who knows? But we'll find out because it's melting. And then there's number 11 that says, you know, when the rising seas rise, when the seas rise, then the melting ice shifts, and that has an effect. And just the whole idea that if the core of the Earth and the mantle of the Earth increases, we're talking about positive linear coefficients of expansion due to temperature, which is very small in terms of inch per inch, but when you're talking about 1,000 mile per 1,000 mile, you can get some significant variation in size, and this can cause all kinds of interesting stuff. So these tectonic plates moving, but moving more than usual from a wider range of temperature. All sorts of things can happen. So anyway, those are some of the things, and not to scare anybody, it's just that it's useful to know what's going on out there. That's maybe one of the curses of being someone with some scientific background, that you know some things that other people just don't know and understand. So the question is, what are we going to do with them? And my answer for myself is I want to make sure that as many people as possible know about these things. I want to make sure that they have a chance to think about them, evaluate them, and realize that they're based on pretty solid laws of science. Let's look at comparison now between 2018 and 24 for the United States utility electric generation, okay? Here's what was happening in 2018. All right, natural gas, 35.6%, coal, 27.8%. You can read that. I don't need to say. Let's see what's happening in, and that was a 425 billion kilowatt hours of electricity made. Okay, the amount of energy required to do that with fossil fuels, of course, is a whole lot more than that because of the second law of thermodynamics. And looking at efficiencies in the range of 35%. So 65% of that initial energy gets thrown away as in form of heat in order to make this electricity. Okay, now let's take a look at what's going on here in 2024. Looks like the pie is a little different color. Well, that's just because that's the color that Excel seemed to want to put in the blanks. But notice that natural gas has gone up from 1469 to 1588 billion kilowatt hours. So now the electricity, 38% is in the United States is from natural gas. 20% is from nuclear, and a little bit more than 2018 now in 2024. So 6 years later, we're fixing up those old nukes, not building any new ones, but we're making sure the old ones work. And they don't give off any greenhouse gas. They've got their other issues in terms of cost, but they're still working, and we're probably fortunate that they do. Coal, notice though, has dropped from 27.8% or 1,146 billion kilowatt hours to 710 billion kilowatt hours. So the utilities, for whatever reason or other, are figuring out that is a better deal for them to switch over from coal to natural gas. And you can see that's happening here. And notice the renewables have gone up significantly. We're looking at 4,178 billion kilowatt hours in 2024 versus 4,125. So we are increasing our electricity production. And the total renewable production in 2024 was 1,000, or will be, as estimated it will be, 1,045 billion kilowatt hours, which is up 25% over 2018. Now that's an encouraging thing if one believes that it's a good idea to replace fossil with renewable. Total renewable, that includes hydro and solar. And this is information from the United States Energy Information Administration. Okay. So the utilities are working hard to make more reliable electricity and to create a smaller amount of greenhouse gases, as we'll see in the next slide. All right, so let's look at the CO2 production, 2018 versus 2024. And you notice 2024, utilities, coal is now 53.1% of their greenhouse gas production versus 65%. Natural gas is 46.9% instead of 33%. All right, but overall, their total is 1.34 gigatons instead of 1.77. And that's a 24% decrease. So we have to give the utilities credit. If we all did a 24% decrease in a matter of 6 years, I think we'd see some things happening. So we need to look at if the utilities can do it, and if they see that it's economically feasible and practical, what about the rest of us? And what about all the other sectors? All right, well, let's look at these other sectors, okay? 2023 United States primary energy consumption by sector. Electrical generation, 34% of all the primary energy in order to generate 13.2 quads, okay, out of 32.1 in, 13.2 out of electricity, and that goes to everybody else and keeps the lights on in the offices of the utilities as well. Transportation, 28 quads, and 37%, and less than 1% of transportation is using electricity right now. Industry, 26.1 quads, 35%, okay, of the energy consumption. And this is primary energy consumption. This does not include the electricity. The 18.9% of what industry consumes is electricity that comes from the electrical generation sector. All right. And residential, 11.3 quads with 15% electric. So then so where does the electricity? Well, that's your natural gas heating and natural gas cooking and basic fossil fuel use for heating and residential. And then there's commercial. And commercial is now 50% electric, 50% non-electric. So different from the way it's been in the past. Things are changing. Keep in mind that a quad is 293.0832 billion kilowatt hours. If we want to do some conversions here, the overall electricity conversion, you notice, is 41% efficient, which is better than it used to be. A lot better. 35% is now 41%. Not too bad, 59% still going out as heat. Nice if you could use that waste heat for district heating in the winter. And it goes to all the sectors. Okay, so just so we understand that electricity is making electricity that other people use. And here's your numbers, okay? So primary energy sources, 38% from petroleum, 38% from natural gas, 9% from renewables, 9% from coal, 9% from nuclear. That's the current mix here in the United States as of 2023, which is just about now. So the total primary energy, 93.6 quads. Okay, So there's some numbers, and of course you're going, what in the world are we gonna do with these numbers? Well, of course, you're gonna spit them out at dinner tonight. I mean, what else? I mean, people are gonna wondering, what should we talk about? Should we talk about the election tonight, or should we talk about the election tonight? No, 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 we're gonna talk about US primary energy consumption by sector in 2023 tonight and get over our business. So here you got this slide, you can take it to dinner with you tonight. All right, and so we got 18.9 quads of losses. Just might as well add that in. But what about carbon dioxide production in 2023? Well, here it is. Residential MMT, that's 1,000,000 metric tons. Okay. So 6.5 comes out of residential, 5.2% comes out of commercial, 20% out of industrial, 38.6% out of transportation, 29.7 out of electric power. So where's the culprit here? It's all those gas burners out there on the road. That is the big thing to be looking at now. And that is different from what it was in 2018. 2018, transportation, electric power were just about the same. But at this point, transportation is the holdout in terms of cutting back on emission of greenhouse gases. So we'll take a look at that in more detail. 4,807 million metric tons in 2023 of CO2 production. 2019, 5,147. So we're down. So thank goodness for the electric power and the industrial and commercial and residential. But the transportation is the one that's holding us up. But we are making progress. It could be going the wrong direction. Of course, we say now, if we reduce to zero, what we need to do is reduce to the point where the amount of carbon dioxide is being absorbed from the air by the absorbers, the trees, the green plants, and so forth, is equal to the amount of carbon dioxide that is being generated. So as long as your production equals your consumption, you've got equilibrium. But even though we're dropping this CO2, we still have a long way to go before we reach the point where all of it can be absorbed by the environment. We're roughly 10 times above the point where it can be absorbed by the environment at this point. So, interesting things to know. 2023 U.S. transportation carbon dioxide by sector. Personal vehicles, 58%. Large trucks, 23. Ships, air travel, rail, others, like farm implements, farm tractors and stuff like that. All right, so this gives us, you can't solve a problem without defining a problem. And here it is right in front of us. The problem is basically if we can work on personal vehicles. And I have to say, I was very pleased. I was at the doctor's office earlier today, new doctor, new building. And they had a lot of EV chargers in that parking garage, and there were a lot of EVs parked at those EV chargers. And I almost didn't find a spot to park my own in. But I did, and I came home with a full tank of electricity. Well, it wasn't full by the time I got home. In any case, here's where it's being created, and here's where the engineering opportunities lie. All right, let's look worldwide, because people will say, well, even if the United States does it, what about the rest of the world? What are they going to do? Well, here's a picture. Worldwide, we're looking at crude oil, coal, natural gas, nuclear, hydro, and other renewables, and the trends. And the key here, notice, it's really pretty exciting around 2028, what is going to happen, because, and you've got a logarithmic scale there on the left-hand side of the primary energy consumption. Crude oil has been at the top of that scale for a long time. You can notice that coal started catching up to it there right in the 2015 range. But now coal seems to be working its way down. Natural gas seems to be working its way up. There was a little dip there during pandemic times. And I'm not trying to say we should have more pandemics to reduce our CO2 production, but it did happen because nobody went anywhere, and that made a big difference. You can see it here. But the key here is look at that green line, and that is relatively steady exponential growth that's been going on. And if that continues, and it has been continuing for a long time, and it appears that it will continue, then up around 2028, we're going to have an interesting situation where all of a sudden those renewables, and if you add to that the hydro, and by the way, hydro here is now separated out from the other renewables, the wind and the geothermal and the photovoltaics. Photovoltaics and wind being the two major providers here. But geothermal in certain areas being very, very important, especially in the Arctic regions where there's not a whole lot of sun in the wintertime, although they have some wind, thank goodness, as well. So a lot of interesting things up around when the decade comes to an end that are possible here. And this is worldwide. All right, so what are the other folks doing out there? Well, let's take a quick look. And by the way, here's the numbers for you for 2023, if you want the numbers. And the source here, by the way, the no carbon dioxide sources, there's 18% of those now. 18.7% of these sources are not giving off carbon dioxide. Source here, and notice the source, British Petroleum Statistical Review of World Energy and Nuclear Energy Institute. BP started this thing going way back in the 1980s, and now the Energy Institute is picking up from where they left off in collecting the data. But even BP was aware of what was going on here way back, and now others are taking over the data collection. So again, a very interesting curve, and I'm sure that everybody at dinner tonight will enjoy seeing it. And be sure to feedback to the host today how that went out. Well, let's look at some. Let's have some fun here. Let's do a scenario about carbon dioxide reduction targets, okay? And let's say we just have reductions in transportation, electrical generation, and industry. Transportation, electrical generation, and industry, and residential, commercial stay the same. They don't have to do anything, okay? If we do that, then what would the curve look like? Well, if we do this little thing here, and notice that the orange ones are the same because that is the residential and commercial part of this. And what we see is the blue part, the transportation, electrical generation, and industry. If we have this kind of a reduction, and what can we figure out a percentage there? Well, let's take a look. Starting on the vertical scale, which this time happens to be linear, and we're looking at, like in 2023, for about 4,250, 4,250, and then we're down to about 4,150. So what is that? That's not a huge percentage decrease, is it? 4,150 over 4,250? 4,150 divided by 4,250? Why, that's only a 3% drop. But if we do that annually, by 2038, we've gotten rid of it all. The question is whether we can do it. Well, we're going to do a financial model now and see what happens if we do that. We've seen what the reductions were between 2018 and 2023 and 2024. Well, here's a scenario now that we're going to play with. All right, there's one scenario. 2.5% decrease, okay, followed by additional 15% annual decreases as we go down. Okay, so and why is that? Because 2.5%, if that same initial 2.5%, the second time around, that becomes 2.875% because it's the same amount being reduced from a smaller number. And then 3.306%, again, the same amount of reduction, but you're reducing it from a smaller amount that you're starting with, okay? So And you can have fun with this with your Excel program. Draw your own scenario. But this one is well, then you figure out, can we afford it? Okay, and can we do it? Well, let's look at scenario 2. That would be if everybody reduces equally. Well, that means by 2038, we're done with everything, even the production from residential and commercial, okay? And that's, again, the initial 2.5% reductions for everybody, followed by additional 15% annual decreases, okay? And that's simply because of you're doing 2.5% of a smaller amount, okay? So interesting math. So the third scenario would be 2% annual population increase, because after all, wait a minute now, we're going to be adding more people, so can we possibly do that? Well, if we include the previous scenario and then add more population such that we're doing this on a per capita basis now, and the 2% annual population increase is a reasonable number. That's about what it's been. And there is some evidence to project that the annual population of the United States and other developed countries is going to level off around the year 2075. So we're still looking at down to zero in 2038. All right, even with population increase, an important thing to take into account. Okay, so additional 15% annual decreases after later on, but we start out at 2.5% for the first 1, 2, 3, 4, 5, 6, 7, 8, 9 years, and then we start doing 15%. Okay, by 9 years, we're presumably ramped up to where we can make a much bigger dent. And, you know, it makes some sense. We could go 2.5% one year, 3% one year, and so forth. But this just goes 2.5% and then jumps into 15% decrease. And again, if you do this on an Excel spreadsheet, you can put in whatever numbers you want and see how they come out. And then you do a financial check to see if we can afford it. Like this. Challenge number 1, transition electrical generation to renewables. And that means we would need to eliminate coal and eliminate natural gas. And that's about all the fossil fuel that's being used now. We don't use much of, I mean, a very small amount of petroleum is used to make electricity and diesel generators, but most of it is coal, natural gas, nuclear, and renewables. And the CO2 emitters are the coal and the natural gas. So we need to replace 0.716 trillion for coal, and we need to get rid of 1.588 trillion kilowatt hours with renewables. And we're going to need some storage to handle the stabilization, because somebody once observed that the sun doesn't shine at night and the wind doesn't blow all the time. So we're going to have some storage to levelize this thing out. But analyses have been done, and something like 100 million kilowatts of storage, and that's somewhere in the neighborhood of maybe 200 million kilowatt hours of storage that comes in 3 different versions: short-term, medium-term, long-term. But for the moment, let's just look at the numbers here, and we'll come back to some of these things in more detail. Now, average renewable installation cost is now about $1,500 per kilowatt. All right, and there's an asterisk that will say something about that. We're saying average. That means utility, rooftop, wind, solar, geothermal, and so forth, okay? Now, the average renewable energy production is about 1,500 kilowatt hours per year per kilowatt. That first 1,500 is assuming 80% utility scale, 20% small scale. Average renewable energy production, 1,500 kilowatt hours per kilowatt per year for a nice south-facing array. Some of the arrays will produce a lot more than that, but others will produce less. On average, 1,500 is not a bad number to use for doing an analysis. So therefore, every 1,000 watts gives you about 1,500 kilowatt hours a year. Costs about $1,500 to install it. All right. or in other words, about $1 for every annual kilowatt hour, whatever that means. Well, that means each of those 1,500 kilowatt hours is going to cost you $1 for that year. But then again, it's going to last for more than a year. So then for 2 years, it's down to 50 cents. And 4 years, you're down to 25 cents. And on it goes. The longer it lasts, your cost gets divided up over a longer time. All right. So cost of eliminating coal, doing these numbers, $1 per annual kilowatt hour. That's $0.716 trillion. Boy, that seems like an awful lot of money, doesn't it? And if we want to eliminate natural gas, that's another $1.588 trillion. Now, this is over the entire period of eliminating, and that was something like 15 years, wasn't it? From 2024 up till 2038, so 14 years. All right. So if we amortize this over on an annual basis, it becomes a little bit less per year. And if you spread it over 10 years, it's $230.4 billion a year. So can we afford $230.4 billion a year? Let's look at some budgets. Oh my goodness. The United States gross domestic product is 28.3 trillion annually, and the United States annual military budget is $842 billion. So is that about, well, maybe 30%? 3 times 3, 9, 69. No, it's less than 30% of the military budget. So maybe we can afford this. Let's see, there's something in Q&A. Let me look up there. I'm sorry. Let's see what we've got here. Are those estimates costs for US or global? These are United States numbers, but we're going to take a look at what's happening globally as well. Because we have to figure out if we can do it, can everybody else do it? So Don, that's a good question, and we're going to get there. So soon we'll have an answer. But certainly if we can't do it in the United States, we can't expect anybody else to do it either. I have an interesting observation about China that we'll share in just a minute. Okay, let's see. Click the done button. And by the way, let's see how many, we've got 9 participants today. So if I don't answer your question, if I miss my Q&A box lighting up, feel free to open up your mic. I think that's possible. And you can just say, hey, Roger, excuse me, I have a question or a comment. This is an interactive session here. And it's a whole lot more fun if we have interaction. Let's see, 250. Yeah, we got a little time left. Okay. So in any case, it's interesting to compare things against the military budget. And of course, there's a lot of that stuff going on right now. And one might wonder if we had renewables, then we're not fighting over the non-renewables and the fossils, and which is part of the problem here with importing all these fossil fuels from not so friendly other countries. If we didn't have to do that, maybe there would be a little less tension involved. That's part of the tension with the United States natural gas now being exported to other places. So that's going to be interesting, politically, militarily, and everything else. Maybe part of this military budget could actually be used as an investment in peace, because I've never heard anybody want to go invade somebody because they got too much solar energy or anything of the sort. Nobody's ever fussed about the Iranians building solar. A little concern over nuclear plants, but solar plants, nobody's ever fussed about it, neither Chinese or anybody else. So, you know, very interesting other implications here beyond the money part. But here's the money part anyway. Let's take a look here. What about the economics of energy storage? This, by the way, is an interesting system that Tesla built in South Africa, not South Africa, South Australia, back in 2017, late 2017. They had 100 days to build it, or they had to give it free. They built it in 92 days or something like that. It is 100 megawatts of power available instantaneously, almost within seconds, and 120 megawatt hours. But battery storage is not the only one. There's pumped hydro out there, there's compressed air, there's double area capacitors, there's flywheels, at least 10 different battery technology, electric vehicle excess battery capacity, lifting cement or steel or other heavy weight, weightlifting. A lot of different storage methods out there that we cover in different webinars. But if we talk about the economics of storage, these are commercial methods here, and they wouldn't be out there commercially unless they felt they could make some money on it. So it simply means they're cost effective, and the typical present storage costs about $1,500 a kilowatt for small systems, and less for larger systems. Now that's for kilowatt deliverable, and I thought storage was energy that you stored. Well, but you have to take it out at a certain rate because what you're delivering to people is power. And yes, energy too, but they want it at a certain delivery rate. So with storage, power and energy both become important considerations. So it's about $1,500 a kilowatt. And the kilowatt hours is the available energy. We recognize the difference between power and energy here. So what's it boil down to then? Well, here's some of the storage methods. There's pumped hydro up there in the left-hand corner, and some battery storage, and that thing in the lower left there, that's a big flywheel. And the lower right is it's battery storage, but it's a flow battery instead of a lithium battery like you see up in number 342 there. So let's look at some numbers. 4 hours at 1,000,000 kilowatts and 400 million kilowatt hours. $1,500 a kilowatt, that's $600 billion. And the number of kilowatt hours depends on the technology. Now that's $600 billion. Wow, that's a lot. But again, spreading it over 10 years. We also have to realize this is available on a daily basis. These things cycle. They fill up, they drain out. They fill up, they drain out. Fill up, drain out. And so part of the costing of these things and the pricing of these things is how often, how many cycles can they undergo before they wear out. And we're doing that experiment with our electric car to see how many charges we can charge it and discharge it. And so far, in 6 years, it's showing a little bit of wear and tear, but it's still doing fairly well. But in any case, between filling it up and emptying it out, the number of kilowatt hours over the lifetime of the battery now seems to be the way they're mostly being measured. But if you deliver those kilowatt hours faster, then it does tend to shorten the life of the battery a little bit, because the faster you deliver it, there's internal resistance. That's I squared R heating, and those batteries heat up. And if they get too hot, they can damage some of the chemistry and affect it to change it. So in any case, you store it when the extra energy is available and feed it to the grid when the energy is needed. So there's some short-term, some long-term, and here's your definitions. The storage can be local, neighborhood, or regional. And interestingly enough, electric vehicles can contribute a significant amount to storage need. If you do the math, 100 million electric vehicles, each of which can donate 5 kilowatts and 5 kilowatt hours a day. That's 1 hour's worth of discharge of a 100 kilowatt hour battery bank between 4 o'clock and 5 o'clock in the afternoon. That can provide 500 million kilowatts and 500 million kilowatt hours. And that is a daily thing that can be provided just by electric vehicles. And then they drive home and charge up at night when there's excess capacity available from wind or nuclear. So interesting stuff. And this is good engineering stuff, because it's really neat to do the analysis on this. And believe it or not, this is the kind of stuff that I actually do in my, so I don't get bored at being 81 years old. I work for a former student, and I sign off on the designs of photovoltaic systems. And in the process, a guy gets interested in this other stuff as well. And the math is fascinating. So I encourage you all to do the math. Of course, I almost sound like a college professor here, which, matter of fact, I was for 35 years. So I always encourage my students to do the math and do the thinking, and don't work hard, but work smart. So anyway, here we go. Let's look at vehicles and fossil fuels, because we were fussing about this earlier. Gallon of gas gives off 19.6 pounds of CO2 if you burn it. Okay. Coal generated electricity, 2.2 pounds of CO2 per kilowatt hour. Numbers put in your pocket. You can look these up on the web. They vary a little bit. It all depends on the overall efficiency. But these are nice averages that pretty well coincide with the numbers you'll see on any of the legitimate websites. The nice thing about natural gas, so you can see here's the difference that the utilities see: 9/10 of a pound per kilowatt hour versus 2.2 pounds per kilowatt hour. You cut your CO2 reduction in half by making those kilowatt hours with natural gas instead of coal. So natural gas is a very nice transition fuel. But they also see that if they continue that transition using wind and solar, they get down to zero ultimately. And of course, there's always the cost of construction, decommissioning, and so forth. So then it's a matter of how long does this system have to operate to pay for its initial CO2 cost, which now is in the neighborhood of 2 to 3 years. Okay, so let's see, and that goes for electric vehicles as well. Renewable generated electricity does not release any CO2 per kilowatt hour. We knew that. Gasoline cars average about 25 miles a gallon. Gasoline car, about 80 pounds per 100 miles driven. Electric cars get about 3 to 4 miles per kilowatt hour. And depending on how you drive them, just like with a gas car. So natural gas, electric cars on natural gas electricity, they release about 25 pounds, or they are responsible for the release of about 25 pounds of CO2 per 100 miles driven. So compare that with 80 pounds, and that's not so bad. That's a pretty significant reduction. And as the utilities continue to reduce their carbon footprint, this results in electric cars also reducing their carbon footprint. And of course, electric cars on renewable electricity, 0 pounds per 1,000 miles. Electric versus gasoline. I'm going to click through this kind of quickly. Again, your electricity cost might be different from 15 cents a kilowatt hour. Your gas cost might be different from 450. Put in the numbers that apply, you know. We're engineers. We're allowed to do that. We can do the math. Here's your gasoline vehicle, 400 gallons for 10,000 miles. About $1,200 at $3 a gallon. And at $4 a gallon, of course, it's $1,600, but gasoline has come down from 4 to about 3. 7,840 pounds of CO2 release. That's a lot. That's 3.56 metric tons. In fact, if you do that for the whole fleet of 275 million, that's a lot. 2.16 trillion pounds of CO2 a year. So you see where that transportation vehicular CO2 is coming from. And it's, again, the math is pretty straightforward. This is the United States, but these numbers, they apply no matter where you are, whether the United States or elsewhere. But the cost may be different. So what other form of travel is there? Electric buses, trucks, trains, they're out there. There's that Tesla truck. I saw one the other day. Boy, do they look weird going down the street. Really interesting. Electric trains. But it's not just trucks, buses, and trains here. We got other stuff. We got these cute little bikes. Go down to university campus. Go outside the United States. And you're going to find stuff like this. Smaller. Boy, I see these electric unicycles, electric skateboards, electric scooters, electric everything. You just go to university campus, you see all kinds of stuff. When the rage over electric vehicles and cars, I think people are overlooking the fact that an awful lot of bicycles are being electrified. And all you need to do is go to New York City and see that. Here's the Q&A. Let's take a look. Hold on. Hopefully you'll include construction, manufacturing, carbon costs too. Of course. Yeah. Let's talk about construction manufacturing right now, because that's an easy answer. It's easy to calculate the amount of carbon dioxide involved in the construction of, say, an electric vehicle, a solar system, whatever. For a solar system, the carbon payback time, the carbon dioxide payback time is about 3 years. And it's getting smaller as the amount of energy used is less. And for that matter, it depends on where your solar panels are made. If they're made in China, there's more coal-fired electricity in China at the moment. If they're made in Europe, Europe is the most efficient and least carbon dioxide emitting electricity. So your European solar panels are less than half the carbon dioxide footprint as your Chinese panels. But even with the Chinese panels, the payback period is about 3 years in terms of the carbon dioxide you do not produce, or you're not responsible for having produced by others over the remaining 25 to 30-year lifetime of that system. And you did the same kind of numbers are about true for the electric vehicle. There's a little bit of additional carbon costs in the construction, but the carbon savings, you've seen the savings in the operation of the vehicle, and that doesn't even count the maintenance of the vehicle. Maybe you replace your tires somewhat more frequently, but your oil changes are essentially non-existent, and just think of the number of parts. Of course, that's another problem for the dealers. They have to figure out some way to make that money that they used to get with their monthly and yearly and annual checkups and oil changes and all the other repairs, which are not necessary now in electric vehicles. So, Don, if that is what you were wondering about, we will say that for the moment. But if you want to talk more about that, I'm fine because this is an important question that people ask: is what's the energy payback time on these various things? And the energy payback time are the energy used. How long can you generate the amount? How long does it take to generate the amount of electricity that it took to create this thing in the first place? But the CO2 payback time, if in fact you're creating something with CO2 free electricity, then the payback time drops a little more. Okay, yeah, it definitely brings it up, and then gets the mining and all that stuff. But the mining is included in the number that I just gave you there. There's so many myths. We're going to look at myths at the end, and this is one of the things that I think every engineer needs to know the facts on it. And there's some facts are disputed, but these are some that these are the numbers are in the chemistry. I mean, CH4 plus a certain amount of O2 gives you a certain amount of CO2 plus a certain amount of H2O, and you got to put the numbers there to balance that equation. And there's no change in that in terms of other than in terms of the efficiency of the combustion. So yeah, thank you, Don. I appreciate questions, and I like hard questions even better than easy questions. So other forms of carbon transportation, and we're focusing a lot of transportation because you see that's now where the biggest problem lies in CO2 production. So, but wait a minute, if we're going to make these electric vehicles, how much more additional renewable electricity will we be needing? Well, there's a good question. We better answer that one too, because this was not included in the estimate we did before. So let's take a look. We wouldn't want to let this go by the wayside. Somebody at dinner is going to ask you this question. So now you want to be able to answer it. How much will it cost to replace petroleum with electricity for these cars? Well, let's say we drive a car 10,000 miles a year at 4 miles a kilowatt hour. All right, pretty reasonable assumption, maybe 3.5. It all depends on, see, you'll hear different numbers. And the 3.5 miles a kilowatt hour is if you're running your air conditioner, if you're running your radio and doing all the other electrical stuff, plus if you're maybe proven that your electric car is a little bit hotter than that Jaguar next to you, starts and stops and stuff, you can cut your mileage down a bit. But the driving mileage alone without the other stuff, if you want to be a more realistic use, 3.5, that's about what we get with ours when we include the air conditioning. So, and again, the exact number is it's the process here and the procedure. You can put in more accurate numbers as you get them, but when you see that Tesla advertises a 100 kilowatt hour tank will give you 400 miles, that's kind of like 4 miles per kilowatt hour. All right. And but they'll also tell you it's a little different in the winter, not a whole lot different, because once you start using that battery pack, the electricity leaving the pack with the resistance in the pack warms the pack so that it's not cold anymore, and it then operates more efficiently. Okay, that's an aside. 2,500 kilowatt hours a year per vehicle. So what's it going to cost to make that? 688 billion kilowatt hours per year for the fleet. Well, we did the numbers on that, didn't we? So coal and natural gas for the 2304 billion kilowatt hours at a cost of 2.304 trillion. Well, it means 688 billion kilowatt hours per year should cost 688 billion. Okay. We're talking about $1 per kilowatt hour per year here. That's what we just showed in a previous slide. So again, 688 billion, a lot of money, but that's 68.8 billion spread over 10 years. And the fact of the matter is, it's going to last longer than 10 years. So maybe we're okay anyway at the cost of adding that. Basically, that just says that for my particular vehicle, I need to put about another 1,500 watts on my roof. And this is stuff I do every day of my life, 8 to 10 different sets of plans for 8 to 10 different residences. Typical residence is installing somewhere between 10 and 15,000 watts. And that's typically enough for their total residential electrical load plus charging an electric vehicle. So it can be done on a rooftop is something that's important to know. And that's covered in other webinars as well, but just it's important to know whether you can really do this stuff. And you asked that question, and yes, it is. And 68.8 billion per year is cheaper than the cosmetics industry. So ballpark estimate, because energy efficiency, as we get more efficient air conditioners, the super high efficiency air conditioners that are coming out now, hybrid water heater, convection cooking, LED light sources. I mean, when you think about it, the energy efficiency is going to reduce the need for electricity significantly on a per capita basis. So we may not even have to spend this much because some of that money might have just gone into energy efficiency. So let's talk about these buildings, these zero energy buildings, okay? Doesn't mean they don't use any energy. It just means they are net zero energy building. All right. And here is the drawing that shows what we got. We got a boundary of the site. We've got something there, whether it's just one building, whether it's an entire campus served by a single substation, whatever. It has to have a renewable energy source produced on site that supplies a significant amount of energy to the energy using segment. It's going to have some delivered energy, and some of it could be renewable. Here in Florida, a number of places, the component of renewable energy and electricity now is exceeding 10%. So then the difference between the stuff you produce on site and the stuff you have to buy, whoops, I went backwards, is your net exported energy. And as long as the next exported renewable energy is zero, in other words, as long as you make as much as you buy, that's considered a zero energy unit. Well, okay. So what about costs on that? Again, we don't do anything unless we can afford it and the loans make economic sense, as long as Wall Street loves it. Okay? So let's see how you do this. Here's the source energy conversion factors, first of all, because we already established that if you're going to make electricity, you only get about 1/3 of the or 40% of the electricity back out of the source energy that was involved in creating it. So if you're going to export electricity from another source, you have to be fair. You have to give it a factor of 3.15. Natural gas, different story, because if that's in a gas water heater, then you're not going to lose as much, maybe 9% and more 90% efficiency. And so basically you're looking at efficiencies here of propane, gas, fuel oil, hot water, chilled water, coal, and other stuff. And in the specific use, whether you're capturing all the heat generated or not. So these conversion factors are generally agreed upon by the industry that is designing zero energy buildings. So let's look at some numbers. Let's say that the first thing we have to do is figure out what the direct building energy is going to be. And we need some numbers then. We know that a BTU raises the temperature of a pound of water by a degree Fahrenheit. A kilowatt hour is 3413 BTUs. A therm's 100,000 BTUs. Here's the conversion factors you need, okay? And the assumption here, by the way, is that everybody loves math, because whoever heard of an engineer who doesn't love to do math? And I've heard that architects love to do math as well. So I don't know. I'm kind of curious now. Is there anybody in the audience here? If you would, I'm going to show the participants here. If you don't love electricity, no, everybody loves electricity. If math is not one of your favorite subjects, we need to know that right now. So it's okay if you want to raise your hand if you don't like math. Ah, okay. I didn't see anybody raise their hand at all. I realize that may be because you couldn't find the button for raising your hand, but we don't have time to spend any more time looking for that button. And anyway, here's the conversion factor. It's very helpful. So what we do now is make a list of all those sources. All right. When we rebuild this house, whether it's North Carolina or California, wherever, we might want to do a zero energy dwelling. So here's what we do. If we assume the design is such that it uses 7,500 years of kilowatt hours a year of electricity, 500 therms of purchased natural gas. All right, and that's probably going to change, because natural gas is over the next 20 years maybe phased out and replaced by electricity, because electricity, renewable electricity, may be more economically attractive for certain things, like heating water with a hybrid water heater, for example. But let's do it anyway, just so we can show how to use the numbers, okay? Converting electricity to BTUs, 3,413 BTUs per kilowatt hour. That's direct conversion, not taking into account any losses. You need 25 million some odd BTUs a year for your electricity, your natural gas. Well, first we have to convert the BTU to source energy, so we multiply by 3.15. So the source energy involved in this 7,500 kilowatt hours is 80,632,125 BTUs. That's the amount of source energy involved for one house at 7,500 kilowatt hours a year, okay? Natural gas into source energy, 500 therms of natural gas. Here we got 54,500,000 BTUs total for the house, 135 million BTUs. Gosh, that seems a lot. But means we're going to have to offset it some way or another. Let's just do photovoltaics, okay? You can do it if you want to do it with wind or geothermal if you want. But let's assume PV, and let's decide. Let's figure out how big the PV system will have to be to do this and how much it's going to cost. Okay. We use that 1,500 kilowatt hours per kilowatt hour a year again. Okay, so that means if we convert our BTUs to kilowatt hours per year, we're going to need source energy. We're going to need 16,126,425 BTUs per year per kilowatt. Okay. So now we divide the required source energy to balance by the PV source energy, and we get 135. We divided by 16, 125, 126, 40. Bottom line, BTUs per year divided by BTUs per kilowatt per year is 8.38 kilowatts. All right, so 8,380 watts of PV facing south, generating 1,500 kilowatt hours per kilowatt per year will make all of that source energy that you need. So the question is, how big is that 8.38 kW in terms of square feet or square meters? Well, typical array now has minimum 20% efficiency. All right, up to maybe 22%. So therefore, it should be able to produce 200 watts per square meter in a year. Or no, not in a year, in 200 watts per square meter is an instantaneous thing. Okay. And so 8,380 watts divided by 200 watts per square meter is 451 square feet of south-facing roof space. So divide that up into whatever shape you want, and that's not an unreasonable amount of south-facing roof space. And furthermore, if you're facing east, west, or north, you can still make electricity with the scattered sunlight and some of the direct sunlight coming in the sunny morning and afternoon and evening. So that your losses looking east or looking west are maybe 15%, and looking to the north, instead of 1,500, your number is going to be more like 950, but it's not that you don't make any electricity, you just make less, which means you need more space, more watts, and of course your dollars per watt then goes up a bit. And but from an affordability standpoint, there's a concept called levelized cost of electricity, and that is you take the annual, the total cost of your electric system over the life of the system and divide it by the total number of kilowatt hours produced by that system over the life of the system. Compensate for inflation and compensate for the discount rate and a lot of other things. And you get a thing called levelized cost of electricity. And the LCOE on solar for residential now is right around 7 cents per kilowatt hour. And compare that with your local electric rate, and you decide whether it sounds like that's worth it. I can tell you that thousands of people are making the decision now that, boy, that sure is worth it, because I save more on my electric bill every month than I pay towards paying for my system. So again, just some useful information that is happening right now before our eyes. If you're using 300 watt modules, those are pretty small, but it would be 28 modules. More likely, you're going to use 400 watt modules. All right, so 8,380 watts divided by 400, you're down in the low 20s instead. But at 20% efficiency, the 300 watt module is going to be smaller than the 400 watt module. Will be 75% of the size, so you'll take more of the 300 watts than the 400 watts, but they still take the same space because it's the efficiency per square meter that counts. Okay, so you need to check the dimensions of that module, make sure they fit on the roof, and some roofs are more difficult than others, believe me. Okay, here's some more stuff. Here's this fancy mini split air conditioner we've been talking about, or I've been talking about. I bet most people know about it now. People didn't used to. You can get these things now with an SEER up to 38, and they work down to minus 13 Fahrenheit. I can remember 20 years ago, if they worked down to 40 degrees Fahrenheit, you were lucky. But now we're SEER of 38 working to minus 13 with no additional exterior heat source when it gets really cold outside. No duct work, all your piping to the various outlets around the house, to the basically the air handler is that unit on top, the IC sensor 3D. And so it's a little different decoration rather than an air register. But you got refrigerant lines running instead. The savings is incredible. Well, what's this creature up on the upper right? Well, that thing happens to be an energy recovery ventilation unit. And, you know, ventilation is important. You need outside air. Other stuff builds up inside, whether it's pathogens, whether it's CO2, whether it's delicious garlic smell from dinner, whatever. So we're constantly, and there are ventilation requirements in a lot of buildings where you have to have a certain number of cubic feet per minute per person of occupancy. Well, wouldn't it be nice if you didn't have to bring in outside air and then heat it up? Why not let the air that you are venting out and replacing help the incoming air to achieve an enthalpy closer to that desired inside? And so there's the energy recovery ventilation unit that will do that if you need to have some removal of water involved. This will have a condensate drain, okay? It's basically a countercurrent heat exchanger. The one down lower right, heat recovery ventilation, if humidity control is not so important. This could be in the northern states, in the western states where it's not quite so humid, and you're bringing in air that is above the dew point, then you don't need to worry about squeezing water out of it. But in any case, very clever heat recovery stuff. And more newer houses are being built with this stuff as the builders become aware and realize that these things sell when people find out what their electric bill is going to be in their mortgage in a comparison. A good friend of mine here is in the development business, and they are getting into zero energy homes because they see where in fact they can sell more of those than they can sell of the energy hogs. And everybody wins. The efficiency of these things, the ERVs and the HRVs, is more than 90%. Domestic water heating. Again, do the numbers. We had one of the first solar water heaters in town way back in 1974. It was great. Boy, it made 90% of our water for free. Hot water was free. Well, I mean, we had to pay back the time on the solar water heater. It was a good deal because we got a nice grant because they wanted to prove that things worked. Today, the thing that's out there are these heat pump water heaters or hybrid water heaters, as they're called. They use the heat pump principle, but if the heat pump is not heating fast enough, you can boost it with straight electric, which makes it less efficient. So if you can get used to not having to kick in the straight electric, you can have a big advantage of 3.5 or so by using heat from the air, outside air, to heat your water by way of a refrigeration cycle. All right. And so whether it's powered by utility or PV, it can be more cost effective than domestic water heating. And especially if you're a part-time resident of an area, because if you're not living there when the solar water heater is working, that's not being, water is not being used. Whereas if you're making electricity, that electricity, when you're not living there, if you're not using it, it's going to be sold back to the utility. So, I mean, I've got a lot of friends in the solar water heating business, and those who are willing to do the numbers, they realize that one of these might be one day replacing the solar domestic water heaters. Here's the question. Let's see what we got. Interesting, a DHL would cost more than PV to yeah, no, and in fact, the interesting thing about PV here is if PV is half the kilowatt hour cost than from the utility, and if you've got a boost of 20%, again, you can do the math. If you heat water with a regular electric water heater, you know what the math is going to be. If you heat it with a water heating or with a hybrid water heater, then the amount of electricity used is 3.5 or 1 over 3.5 times as much. And so therefore that reduces your electric costs. And then if you make that electricity with solar, which is only half the price of, hey, Don, that's a great question. What if I want instantaneous hot water for a shower? Hey, listen, I have a more or less conventional water heater in this apartment, and I couldn't get instantaneous water for hot water for a shower if I wanted it, because it takes that water time to get from the water heater to my shower. If you want instantaneous hot water for a shower, you either need a recirculating loop or that hot water source has to be right behind the wall. And a lot of times that's hard to do. So yeah, great idea, but let's don't forget where the losses are in instantaneous hot water. The losses in instantaneous hot water are predominantly in the transmission of that water between the point of generation and the point of use. And it's not necessarily during the time of use, but it's after you're done, all that water in the pipe now cools down. And when you turn it on, all that cold water that's coming out used to be hot. So if you want instantaneous hot water for your shower's got to be right next to the water heater no matter what. And that's not easy to, or that's not hard to figure that one out. And again, this math is it's amazing that I never would have believed 20 years ago that making electricity, first making solar electricity and then using it to heat water would be more efficient than using the sun to heat water. But the overall efficiency of 39,000 BTU per day water heater, you can figure that out in terms of this probably going to be 80 square feet. And do the math, and you'll find that the overall efficiency on that's probably 50–60%. And if you got 20% electricity multiplied by 3.5, that's 70%. So your solar water heater has to be cost competitive from an installation and life cycle costing standpoint, plus the heating itself on a daily basis. So it's interesting. And Don, you're asking some terrifically good questions. I really appreciate that. And I hope the answers you're getting are the kind of answers you're looking for. Okay, so here's your water heating heat pump, and it's very interesting. The limitation on these is the rate of heating is roughly 4,800 BTUs for water for the ones that I've looked up. And the 4,800 BTUs per hour, you can do the math again on that and see how long it takes to make yourself a gallon of hot water at 100 degrees for a shower, depending on your starting water temperature. So I'm hoping that everything you see today will inspire you to go and get your slide rule out. Oh, wait a minute, what's a slide rule? And get your calculator out and do some math on these things, because you'll surprise yourself. Most of the conversion factors and things you need are in this set of slides. What are the trade-offs? Well, make building appliances more efficient. We talked about that. You use less solar. So you compare the cost for improving the efficiency, the cost of more or less solar, and balance it out. Do the math. Different orientations for the array. You can add more, 20% more or 15–20% more array on the west side, depending on the slope of the roof. We'll take a look at that in the next slide, okay? All right, and if you're doing building loads, think about those electric vehicles you might want to charge. So let's just look at Albany for array orientation. The best possible array orientation for Albany is the 30% tilt, 30-degree tilt facing south. That gives you optimal performance, but if your tilt is 45, you're at 99% of that. Okay, you can see how the graph goes here. If you're facing south, west with a tilt of 10 degrees, you still only lose 9%. If you're facing west at a tilt of 25 degrees, you're losing 17%. Okay. Now I was going to put north on this graph in that last thing, but that the variation is a whole lot different between north and south of up north at 45 degrees latitude or down south in the 20-degree latitude range. But the number can be something in the neighborhood of say 70% for north facing, as opposed to northeast or southwest. Okay, so it's interesting. Things are cost effective now that were not cost effective 15, 20 years ago. Here's a question. Let's see what we got. Wayne, Albany, New York. Yeah, that's what you mean, right? Albany, New York. Yeah, I thought generally the attendance of these webinars is higher because there's more. The northeastern states require live instruction, so I just figured I'd put a northeastern state in. But these, you can do the numbers here. Now, if you want to do these numbers for yourself, the National Renewable Energy Laboratories has a wonderful simulation program called SAM, SAM. And all you have to do is Google NREL and look for SAM and download it. It's free. You have to give them your email address so they can tell their local legislator that they are giving this away to a lot of people so that the legislature can give them more money for research. But all these numbers come out of the system advisory model. So you can look up for your house wherever you live and whatever orientation you want and vary a whole lot of different things. It's a really fun program. After you are done having discussions about these things over dinner, then you get out SAM and you start talking about SAM. Okay, so let's see. Here's let's take a look. We're talking about zero energy buildings, and I better look at my phone here. 334, we're going okay. Look at the difference. Here we go. Zero energy buildings, 6 different cities. It's not the same everywhere. If we look at Atlanta, we have to pay an additional $19,548 to go zero energy. But in the process, we're going to save $152 a month over the additional mortgage payment of $100. So nice savings. Baltimore, you get out to San Francisco and savings is even better. Now, of course, these numbers change with location, but you can do these numbers. You know, what's it going to cost to do what you want to do? And it's not that difficult to figure out what your savings are going to be and what the cost of money is. You know, every year the Feds just dropped the borrowing rate by half a point, I guess. So now it's a little cheaper again. I think I used 4% on this as a lending rate. I'm not sure. I used whatever it was a year ago. And but anyway, this is the kind of math that you do to see whether you really want to do this stuff. Because some people do things just because they want to do it, but if you want to make money on the deal, it is possible to make money on the deal, and that's important. So if you want to do energy retrofits, look at all the retrofits. We talked about a lot of these things. A lot of these things could use a little engineering advice, and there's a lot of nice computer programs you can use to do the analysis. What if I put new insulation, whatever? Energy Gauge USA is a nice program that you can download from the Florida Solar Energy Center. And it does need, you don't have to do much guessing. You just put in the numbers they ask for. And you run the program, and it'll do a financial analysis for you. They analyze the envelope, the equipment, and then they do cost effectiveness analysis. So you decide what's the most cost effective thing I want to do here. Now, if you want to do the NREL route, you can use the BEOPT, or BEOPT. It's very good for single or multifamily, and it's good for newer retrofits. FSEC Energy Gauge USA, there's 2 versions, one for residential, another one for tall buildings. You can do them on 30-day trial basis. If you like them, if you actually want to get into business, then you pay a monthly maintenance fee like most any other program. But if you just want to see how they work, you can download it for 30 days and do it for your own house. See what it sounds, see what it looks like. Q&A again. Let's take a look. Don, let's see. NREL, only Fred Lab dedicated to right. That's it. You found it just like that. You got two computers there that you were able to find that? You're not taking your eyes off your screen here, are you? Thanks anyway. Yeah, okay. If you want that, anybody wants that website, take a look at your Q&A because Don just looked it up. Yeah, I mean, it's a no-brainer. You simply Google National Renewable Energy Labs and it pops right on up, and finding Sam is almost on the home page. Okay, and if you want to remember the NREL, Sam, it's at the bottom line on this page here. So these programs are really neat. They save an awful lot of time. Q&A. Alt tab switch screens. Oh, okay. All right. You're forgiven. All right. I don't have time to play with my alt tab right now. Okay. All right. So you saw this picture before. What are the challenges to the grid? Well, storage, big deal. Because wind and solar, this is one of the downtimes here. I mean, solar, of course, doesn't shine at night. But even during the day with clouds over a solar array, it's kind of a nightmare for the array. Now, distributed solar is less of a nightmare because when one house has a cloud over it, chances are there's another house not too far away that doesn't have a cloud. And when a cloud on a residential system might make a difference of 5 kW, like turning off a dryer or something like that, or even a range or an oven, or an air conditioner cycling. It's a little bit bigger deal when you have a utility scale field of over 100 megawatts. If you get a cloud over that, that can be a fairly big glitch. So you need to have something to back it up. So one thing that's advancing is battery storage, but there's other storage. I see the chat. We'll come to that in just a minute. And a lot of other storage we mentioned. 100 million EVs themselves can provide 600 million kilowatts and 1 billion kilowatt hours. So it is not that we can't afford the storage. It's possible the utilities are doing it right now. And in fact, if this levelized cost of electricity thing is done with utility scale electricity plus utility scale storage, the numbers I'm seeing right now are 4 cents a kilowatt hour, roughly 1 cent for the electricity and 3 cents for the storage. So that's still pretty cheap electricity for stable electricity on 24-hour basis. But pumped hydro has been around for a long time, and that's another story. What do we got for a question? Oh, okay. It's another story about NREL. Yeah, okay. Okay. I got it. Something about generators. They don't like power. You know, a motor becomes a generator if you try to take electricity out of it. And generator becomes a motor if you try to put electricity into it. And a lot of generators and their prime movers like to just keep rotating in one direction. And so they don't like to run backwards. So there's some interesting issues there. If you have a whole lot of renewables, nothing to do with it, you either have to curtail it or store it because you don't dare let it flow backwards towards your other power source. Because they don't like to run backwards. They are not all happy with that. But the technology is here to do that. So you just need to remember that. Substation voltage stabilization at substation level. That's important because right now there are mechanical transformer voltage caps in a lot of the substations, but if we do some really good stabilization with storage out in the field, then there's not going to be as much fluctuation at the transformer taps. And if we do that electronically, which is also possible to do with large scale power electronics, we can solve that problem as well. So these are all problems that people already know how to solve. So what will it do to the grid? Here's what we've got. Looks kind of like this. We make it, we distribute it, and we use it. Except now we're doing a little more of this stuff where we're generating stuff, storing some stuff, and sending some stuff back to the grid. So future grid, this is what's emerging out there. And we're, as engineers, we're going to be a big part of making sure that this new future grid is going to work right. Now, there's a few other things. Let's take a look at the time here. 3:43. Yeah, we got a little time here. What about government leadership? Well, we've heard a few debates lately. Now, I got some idea of what might happen. But, you know, government is more than just the Capitol and the White House and the Supreme Court. It's also these people out in the streets who are insisting that, hey, I elected you to provide me with certain things that I think are important. And we're seeing a lot of that. And that's part of government. It's part of good government if it's a peaceful protest, because it's the way you get people's attention. I'm not sure how many folks in the audience have been a part of them. I've waved a few signs in my day, trying to remind people that you got to do certain things if you're going to make people happy. And we can green up a lot of government buildings. We can green up a lot of government transportation. Imagine the Postal Service, for example, being greened up with electric vehicles. Incentives for green economy, and the numbers have been done on the Postal Service greening, and it's very impressive in terms of the savings involved. Carbon taxes, other incentives for green economy. Well, should we be spending public money on that? Well, I'm all for parity. If we spend as much money as incentives for renewables as we have already been spending as incentives for non-renewables, then that's okay with me. Or if we just pull them all away so there's no incentives either way. Of course, the problem there is the nukes can't get insurance. So the nukes would go away if we didn't have government insurance. So it gets complicated. Everybody knows that. EV charging at government buildings, it's happening. Greening of the military. Military recognizes that the greener they are, the more efficient they can be. Planning and development, long-term commercial, you can read all this stuff and discuss it at dinner tonight. Some people are fussy about where they put their money. If they put it in certain places, they will lend it to fossil fuel industry, and other people, maybe you'd rather they didn't, and others won't. And some people are paying attention. I will admit to having money in Bank of America. It's convenient because they're all over the place, and we can go to their places to withdraw money. But if you're really serious, you might want to consider some of these other guys. Or you can always stand in front of Bank of America or Citibank with a sign and say, hey, you guys, we could clean up your act a little bit. And one thing that's happening is Wall Street is seeing these numbers that I've just presented to you, and they are discovering that renewables is really a pretty good place for putting money. And it's happening all over the place. We're seeing it in terms of people borrowing money to install photovoltaic systems. It's very popular, and there are lots of lenders out there. What about the gross domestic product? Some more numbers, it's for the fun of it. And this is one of those, you know, scam publications, you know, Scientific American, what do they know? On the other hand, Scientific American has been pretty revered in terms of their factual stuff over the years. They've had some really good stuff. Hey, look at the numbers here. The blue stuff is if we follow the Paris Agreement conditions, and the red stuff is if we don't. And what happens to the per capita GDP over the next 70 years and or 75 years. And you can see that the big loser is going to be the United States if we don't pay attention. Interesting, isn't it, that China is going to benefit because, yeah, they've been making and selling a lot of this stuff. And I want to tell a China story if we have time. I'm going to tell it right now. Because of tariffs, the Chinese haven't been able to export as many of their photovoltaic modules. So therefore, in 2023, year over year, China installed 150% more modules domestically than they did in 2022. That is the highest jump in installations of any country in the world. 150% increase domestically in 1 year. Maybe it's 125. It's a big number, over 100% increase in a year. We were talking about increasing numbers by 2% a year earlier. We're talking 100% the Chinese did because they were stuck with modules that people didn't buy because of tariffs. And that, of course, is a very positive effect because they're replacing some of that coal-fired generation in China. Look at Russia up there at the end. They win no matter what. So, yeah, no, they don't win no matter what. But if they adopt the Paris Agreement conditions, then they win. But otherwise, they lose just like the United States. Everybody's a loser on a per capita GDP. And part of that is look what the insurance bills are going to be. What in the world is going to happen to our insurance now after this disaster that went through the southeastern United States? Somebody's got to pay for that. And anyway, so here's some of the economics, and it's very impressive. And that's why we talk about, what's in it for the engineers. Well, what's in it if we don't do it? A whole lot higher insurance bills for one thing, guaranteed. And we look at United States and China. China looks pretty good no matter what, because first of all, our per capita energy consumption is not nearly what we have here. But if we're going to stay on any kind of a level playing field with China, we got to bite the bullet and get it right, because that's what they're doing. Who's affected most? Well, yeah, Nebraska big time. But we just saw the flooding that damaged other infrastructure now. And so certainly one can't argue with the numbers on this particular slide as well. It's happening, whether it's from climate change or otherwise. It's still money that is going to increase our insurance bills and take away a lot of our spending that might otherwise be discretionary. Greener ethics, yeah, we can do that too. We can do that as design professionals. We can say, you really ought to do this because it's a better deal for you economically, but it's also better for your children, grandchildren, and the planet. Just the fact that CO2 reduction can be profitable should attract a lot of people. And certainly it's done a good job with Elon Musk. Millions of new jobs in clean energy and industry. Yeah, they're out there. I mean, this is another presentation we have, but there's millions of new jobs available. It's our job to convince the clients that it's cost effective to do this. Might take a little longer to get through the permitting, but overall, very effective. And green reduces healthcare costs. Oh my goodness, do they ever? And many other associated costs. This ventilation thing is very important, and you can read up on that. So anyway, a little bit more here. Let's check the time. Yep, we're doing okay on time. What are some of the non-technical barriers out there? Even before I start flashing a few, I saw an interview on TV one time, not too long ago, about a farm person out in Iowa being interviewed, claiming that the cows are sequestering carbon really well. And you know, the implication there being if cows are sequestering carbon, then they're doing good, except for the fact that they are sequestering carbon that has already been sequestered. There is no carbon as such in the atmosphere other than smoke, which settles out fairly quickly. But the carbon in the atmosphere that sometimes is confused, and that's our job too, to help get this straightened out. We are talking about carbon compounds that are volatile, that like carbon dioxide, okay, like methane. These are all things that are airborne, that they are gases, all right, that are held in the atmosphere. We don't see diamonds and lumps of coal floating around as carbon. So we got to be a little careful about the use of the word carbon and what does it really mean. And in the process, sure, I mean, the cows are great. I mean, they eat that grass, they sequester it for a while, and they convert it into manure, which is great fertilizer. I mean, when I was a kid, I lived in South St. Paul, Minnesota, third largest livestock market in the country. And we would get a truckload of manure every couple of years, have them dump it on our front lawn. We'd spread it all over the grass, have the greenest grass in town. So yeah, I mean, cow manure is great fertilizer, but in the process of manufacturing that manure, the cows give off a lot of methane. And so, so actually both parties are right. They sequester the carbon in a form that's useful, but they also give off a fair amount of greenhouse gas. So how do you balance the act on that one? You try to do a payback period analysis, and I haven't seen anybody do that yet. So let's look at some of the other technical, non-technical barriers. How many people say climate change is a hoax? Well, I'm guessing that everybody here has probably heard somebody say that at one point or another. And well, the numbers prove that wrong. And the fact that this is not just something that is not caused by humans, well, we're kind of coming around to that now, that yes, humans are kind of behind this all. And it's the idea that this is a temporary situation is a favorite topic among a lot of people who don't understand the ramifications of carbon dioxide and the sequestering of carbon dioxide and how long it takes for this thing, once it gets out of hand, to come back again. We could be looking at archaeological time as opposed to typical decades or centuries. So temporary is not a word that works here. Oh, and this happened back in the 1800s. Yeah, well, there might have been a dust storm. There were some things that lasted for 10 years. Well, this is lasting a lot more than 10 years. And anybody who lives for the next 50 is going to see some really interesting stuff going on. And of course, the temperature still drop below zero in the north, and there's plenty of snow and cold. Well, maybe there used to be, but not so much anymore. The Greenland ice cap is melting. I was up there on that ice cap about 15 years ago. It was pretty impressive. I'm kind of like to go there again and see if it's what's left of it. I've been watching the ice cap out on the Canadian Rockies disappear for the last 50 years. And that's 50, no, more than that, 60 years. And that's really shocking to see that. Average temperature has not changed. Another very interesting statement. That's just like saying my average age hasn't changed, because I can plot my age for the last 20 years and then take the average and show that the average has been the same for the last 20 years. I can do that and say, well, in that case, my average age isn't going to change for the next 20 years either, or the next 40 years. Because I keep adding other on, as I add a year on the top end, I take one off the bottom end, and the average doesn't change. What's the chat here? Let's see what we got. Sadly, nearly half the voters are considering voting in an administration that doesn't believe in global remedies. Well, sounds like you're on the same side of the fence that I am, Don. And we can't talk politics, but yes, sadly, and I'm not trying to talk politics here. I'm trying to get out the facts. And if you feel this is important, maybe you'll help me. But yeah, It is a real shame because this is the real stuff that we're looking at here. Average temperature hasn't changed. I saw that in a textbook that my granddaughter had in the 5th grade. And I almost, well, I did not react well to seeing that. All we need to worry about is sea level rise. Well, you saw 10 other things, and there's more on that list as well. And if we eliminate fossil fuels, we'll go bankrupt. Yeah, that's another good story. And if we don't, we'll go bankrupt even faster. Let's save some of these fossil fuels for future generations 1,000 years from now. Aren't they going to want to have a look at what we used to do? I mean, my goodness, let's save some souvenirs for them. Okay, so anyway, if we act now, it would be good. And maybe we need to think, well, maybe gross domestic product or gross national product aren't really the best measures of the health of the planet. Or if we operate them correctly, but maybe the greenhouse gas concentration is a better measure. And the fact that reducing GHGs can have positive economic effects, maybe GDP is okay after all. Because doing the GHG thing actually saves the GDP thing. Then there's the plastics. We got to play with those. There's a lot of other stuff out there. There's those social issues. Can use a little bit of work. I hope that we can all help with that. We can't buy the odd thing. When all is said and done, a lot more is said than done. I have a sign on my desk that says that, and we got to get out there and do something. And if we do, our children, our grandchildren, they deserve more than that. I'm proud to say that my 20-year-old granddaughter is now becoming an activist. She understands. So we, the birds, the bees, and all of the living things on the planet deserve more than, when all is said and done, a lot more is said than done. So that's it. Does anybody have anything they want to talk about? If so, feel free to open your mic or go ahead on up to the chat. Here's chat. Let's see what we got. I'm going to leave my chat open. Webinar video. Oh, okay. That's from the host. Okay. Watch out for Edge or Internet Explorer browsers when you get certificate. And if you want to get a PDF copy of the slides, by the way, these are my slides. They show credit where credit is due. And as long as you use them and show credit where credit is due, I encourage you to make whatever use you can that you feel might be useful. Any other chat, any other comments? It's getting late in the day. So let me say that thanks to everyone who participated. I appreciated the comments and the thoughts that you shared. It helps me make sure. And I hope that what you learned today will be useful to you in business and in your social engagements. And feel free to look this stuff up and read up on it because it gets more and more fascinating. It gets scary if you look in one direction, but it gets very encouraging if you look into possibilities, and all we have to do is adopt those possibilities. Otherwise, I went to an anthropological exhibit down in Fort Lauderdale about a month or so ago and realized that if we don't get our act together, there may be some other species that will replace us in another 100,000 years. But I think it'd be nice if we get our act together. And thank you all for being here. Well, Wayne, I'm 2 hours flew by. You may not have noticed it, but I have, well, I'm a retired college professor and teaching is my thing. But I'm also working in the solar industry, and so I'm glad the 2 hours flew by for you. And in fact, I'm surprised it really has. So I hope you get some use out of it. All right. Well then, let's give our hosts a chance to shut down and get out everything that's requested. And wish all of you a wonderful holiday season as it's coming up. Let's hope that some of the destruction that's going on the planet can be replaced by some good quality construction. And hopefully we'll all come out a whole lot better next year and the years to come. Oh, the webinar is over, so it's okay now to sign out. And don't forget to request your certificates. I'm proud to say I finished up my last hours of required continuing ed over the weekend, so I'll be good to go again in February. Diane, I'm glad you enjoyed it.